Good morning, ladies and gentlemen. My name is Chen-Chieh from the Department of Material Science and Engineering, National Taiwan University. Today I'm going to talk about the research entitled Using the Nanoimprint-in-Metal method to prepare corrugated metal structures for Plasmonic sensors through both the surface Plasmon resonance and the index matching effect. In this lecture, I will introduce the background and the concept we use in this research, including the surface Plasmon resonance and the index matching effect. And then I will show you how we fabricate the corrugated metal structure, and we will use it to act as a chemical sensor and a biosensor. And in the last, I will draw some conclusions for this study. The basic concept we use is the surface Plasmon resonance. The surface Plasmon resonance is a collective oscillation of free electrons at the metal and the dielectric interface. And it is usually excited by a Prism coupler, a focused laser beam, or more generally by periodical metal nanostructures. And for two-dimensional metal nanostructures, the surface Plasmon resonance, it will be excited at the wavelength according to this equation. And from this equation, the index P means the period of the structure, and the I and J are the exciting mole number of the surface Plasmon resonance. And the epsilon 1 and epsilon 2 means the dielectric constant of the metal and the dielectric. Therefore, from this equation, you can see that the surface Plasmon resonance is highly sensitive and highly dependent on the environmental dielectric constants. Besides, the surface Plasmon resonance always induces the extraordinary transmission. For example, for a whole array structure on opaque materials, when the diameter of the hole is on the order of sub-wavelength scale, the transmission intensity will be largely reduced due to the diffraction limit. However, for the metal structure, the surface Plasmon resonance will induce the extraordinary transmission phenomena that breaks the diffraction limit in the case of the opaque material. Moreover, if the refractive index of the substrate is identical to that of the substrate, the transmission intensity can be further enhanced, and we call it the index matching effect. Therefore, in this study, we will use the surface Plasmon resonance and the index matching effect of the corrugated metal structure for detection used. To prepare the corrugated metal structure, we use the Nanoimprint-in-Metal method. In the fabrication process, first, we deposit a 70 nanometer thick gold film on a polycarbonate substrate, and then we heat the whole system to the glass transition temperature of the polycarbonate substrate, which is about 150 Celsius degree. And this aims to soften the substrate and make the nanoimprint process more easy and convenient. And then a grating mold having a period of 800 nanometer and a line wide of 400 nanometer is imprinted on the gold film and make the gold film turn into the corrugated morphology. And after we release the mold, we can obtain the corrugated metal structure. And these are the corresponding SEM images and the photographs. And you can see from the photographs, you can see the clear diffraction pattern that arises from our periodical structure. And because we use the polymer substrate, therefore our plasmonic structures are highly flexible. And this corrugated metal structure has unique plasmonic properties. And this figure shows the transmission spectral mapping of the corrugated metal structure at different incident angles. There are just a few plasmonic modes in the spectrum region, which is in contrast to other plasmonic structures that have multiple and complicated exciting modes. Therefore, it will be easy to use our corrugated metal structure to as a sensor because it provides a really simple and clear signal change. Besides, we also show the transmission spectral mapping of the corrugated metal structure at different refractive index of the substrate. There are two modes in the spectral region. One is the surface Plasmon resonance excited at the gold digital film and the PC substrate interface, and we call it the Go and the PC mode. And the other one is the surface Plasmon excited at the Go and the superstrate interface, and then we call it the Go and the superstrate mode. And as you can see, if we increase the refractive index of the superstrate, the wavelength of the Go and the superstrate mode perform the redshift toward to that of Go and the PC mode. And because the PC substrate, the refractive index of the PC substrate, it doesn't change, so the wavelength of the Go and PC substrate mode doesn't move. Besides, as you can see, if we prepare the corrugated metal structure with different imprinting pressure, in the larger imprinting pressure, the two modes begin to overlap in the low refractive index region. Next, we explore the index matching effect of the corrugated metal structure. These are the transmission spectrum of the corrugated metal structure at different refractive index of substrate. As you can see, if we increase the refractive index of the superstrate, the transmission intensity of the Go and the PC mode increased and reach its maximum when the refractive index of the superstrate is identical to that of the PC substrate. And this phenomena provides another criterion for the sensing. That is, if we can measure the transmission intensity of the Go and the PC mode, then we can calculate the corresponding refractive index of the superstrate. And to the best of our knowledge, there's few other plasmonic sensors apply this phenomena for sensing. And besides, it is worth mentioning that because we just want to we can just measure the transmission intensity of this mode. Therefore, we do not need other expensive instruments such as the spectral photometer. We just need a general light source and a photodetector, and it can be detection used. And from this three-dimensional finite difference time domain image, you can see that the coincidence in the refractive index of the superstrate and the PC substrate makes the energy of the surface Plasmon resonance can more efficiently cover into the other side and leading to the enhancement of the transmission. As described above, our sensor provides two criteria for sensing. One is the wavelength shift of the Go and the superstrate mode, and the other one is the transmission intensity change of the Go and the PC mode. These two figures are the dependence of the wavelength and the transmission intensity on the refractive index of the superstrate. And the slope of these calibration curves is the sensitivity of our sensor. And the sensitivity of the sensor could be defined as this equation, where it means that the resonance wavelength shift per refractive index unit. And based on this equation, our plasmonic sensor provides a sensitivity up to 800 nanometer per refractive index unit, which is comparable to other plasmonic sensors reported. And besides, based on the intensity change, our plasmonic sensor provides a relatively linear response to the refractive index of the superstrate. Therefore, we use our plasmonic sensor to act as a chemical sensor. First, we use it to sense the ethanol solution with the different concentration. These are the transmission spectrum of the corrugated metal structure immersed in the ethanol solution with different concentrations. And as you can see, if we increase the concentration of the ethanol, the wavelength of the Go and the superstrate mode perform the redshift, and the transmission intensity of the Go and PC mode increased. And then we feed the wavelength and the transmission intensity to the calibration curve as shown in the previous slide to calculate the corresponding refractive index of the ethanol solution. And as you can see, no matter you calculate the refractive index from the wavelength shift or by the intensity change, compared to the reference refractive index, the mismatching error is very slight. And if we average the refractive index that determined by the wavelength shift and by the intensity change, you can see that the mismatching error is further reduced to less than 1 milli refractive index unit. Therefore, by mutually examining the refractive index that determined by the wavelength shift and by the intensity change, we can exclude some experimental error and obtain more accurate values. And in the last, we want to use this plasmonic sensor to act as a biosensor to sense the L16. L16 is a diol-containing amino acids that are present in important role in many diseases. Thus, the cis detection technique might be very important. And in our detection process, we first modify the corrugated metal structure with a monolayer of the 16. And then we prepare different target 16 solutions with different concentrations. And the target 16 is first conjugated with the gold nanoparticles prior to detection. And then we use the copper ion to bind the 16 to the modified 16 and measure the transmission spectrum of them. And as you can see from the transmission spectrum, our plasmonic sensor provides a relatively linear response to the concentration of the 16. And besides, we can provide detection of limit on the order of 1 micromolar. And in the last, I want to draw some conclusions for this study. In this study, we used the one-step nanoimprint-in-metal method to rapidly prepare the corrugated metal structure for plasmonic sensor use. And our plasmonic sensors provide two criteria for sensing. One is the wavelength shift, and one is the intensity change. And based on the wavelength shift, our plasmonic sensor provides a sensitivity up to 800 nanometer per refractive index unit. And as a chemical sensor, it can sense the ethanol solution or other solution with a refractive index mismatch error down to less than 1 milli refractive index unit. And it can be used as a biosensor as well. We use it to sense the 16, and it can provide a detection limit on the order of the 1 micromolar. And our plasmonic sensors has very much advantage that it is flexible, portable, and easy to use. And even it can be used without any expensive instruments. In the last, I want to thank the National Science Council of Taiwan for supporting this study. And thank you for your attention.